This is problem 8.59, and this problem consists of gases are discharged from a stack to the atmosphere, and gases came from an oven at high temperature. The temperature is 600 Celsius and the mass flow rate is 0.5 kilograms. So the gases are passing through, and we are asked to compute the mean temperature at the outlet and also the temperature of the surface of the pipe and the outlet. Now this chimney is outside, and then the ambient conditions are a temperature of 4 Celsius and the velocity of the wind is 5 meters per second. So the first thing that we need is to identify that we have a combined convection here. So we have internal convection because of the gases inside the pipe, and we have an external convection because of the air from outside is cooling down the pipe. So we'll need to compute an overall heat transfer coefficient. So this problem actually corresponds to this type of problem in which we have an inner flow and outer flow. So we need to compute the total resistance. The resistance consists of internal one due to the convection, internal convection, for which we have to find out what is the convection coefficient. Some part that is the conduction in the pipe, and the external convection, which corresponds to external flow, and we need to find out HO. So the total resistance can be replaced in our equation. So this is the equation for our pipe. So instead of having the H coefficient, as usual, we have an overall heat transfer coefficient, but we can express that in terms of the resistance as by replacing UA as 1 over the total resistance. And the total resistance is given by the 3 components. Now, as we discussed before, the middle term is approximately equal to 0 due to the fact that the inside diameter and the outside diameter are more or less the same. So this is approximately equal to 1. So natural log of 1 is 0. And also, if the material of the pipe is highly conductive, this K is a large number. So we have one number divided by a large number is also a small number. So this is depreciated in those cases. In fact, for our problem, we are not even given the internal diameter and external diameter. We have been told that the diameter of the pipe is equal to 0.5 meters. So we have to count with that. So we need to find out it's just the internal and external heat transfer coefficient. So for the internal, so we need we need to find out the properties of the gases. In this case is air. So we have to find out the average of the mean temperature, the average of the mean temperature. And so we start with 600, which is the temperature at the inlet. The temperature at the outlet, we don't know. We know that it's cooling down, and we don't think it's going to cool down to 5 degrees to the outside temperature, but it's less than 600. So I put 500. In case if the result is too different to 500, so we have to come back to this point and put the temperature that we got and compute the properties for this average of the mean temperature. So with the average of the mean temperature, we go to table at this temperature, which is equivalent to 823 Kelvin, and we compute the specific heat, viscosity. Well, we copy the conductivity and Prandtl. We do a similar thing for the external fluid properties. So for the external fluid properties, we have the film temperature, which is the temperature in the surface plus T infinity divided by 2. Now, the temperature of the surface, still we don't know. But I'm going to put the same value of 500, assuming that this is metallic, and so we are going to have values in between 600 and the temperature in the exit. So that will give us 250. It's much more wider range in this case because it's 504. And with that, we go to table A4 again and we copy these values. So again, if after we compute the temperature in the surface and we find out that there is two different, we can recalculate the values and iterate a second time until we get much better values. Now that we have the properties, the next thing is to do the analysis. So we use our equation for constant temperature on the pipe, and so we have delta T at the exit divided by delta T at the inlet, which is T infinity minus the mean temperature in the exit, and T infinity minus the mean temperature at the inlet. So this is equal to e to the minus area multiplied by the overall heat transfer coefficient, or we can replace this by 1 over R, divided by the mass flow rate Cp. I'm going to use U, and I'm depreciating the resistance of the pipe. So this is 1 over H inside divided by plus 1 over H outside. And so we have to compute the internal and the external flow. For the internal flow, so we need these values. So this is what we need to find out. So for the internal flow, then what we do? We compute Reynolds. So we need to know if it's turbulent and if we are in the entrance. So Reynolds is 4 times the mass flow rate divided by pi d mu. So if we put these values in the calculator, we get 33,826. So that means it's turbulent because it is higher than 2,100. Okay, and so we have the equation for turbulent flow. So X fully developed hydraulically is 10 times D. So 10 times the diameter, which is 0.5, is 5 meters. So this is the entrance. The total length of the pipe is 6 meters. So therefore, it is fully developed at the last part. At least at the last part is fully developed. So we can use the Ditus-Volter equation. The Ditus-Volter equation is Nusselt D equal to 0.023 Reynolds to the 4th over 3. This is 4 over 3. Multiplied by Prandtl to the 0.3 and 0.3 because it's cooling. So we got Nusselt D equal to 10.2. Now Nusselt D is equal to H, and this is the average, so this is H multiplied by the diameter and divided by K. Okay, so we can solve for H, and we have that is Nusselt D multiplied by K and divided by the diameter. And by replacing the values, H, the average H is equal to 10.2 watts meters square Kelvin. Now for external flow, we compute our Reynolds, and this is Reynolds also based on the diameter because it's Reynolds around pipe. So we got 94,660. Now I'm saying it's laminar. Yes, because it's external flow, and so this is less than 510 to the fifth. So for external flow, the conditions for Reynolds is different than for internal flow. So we go to our equations for external flow, and we found Churchill-Bernstein, and it's telling us that with Churchill-Bernstein, nozzle D is equal to 205. Then we can solve for H, and we got a value of 13.9. Or if we use Hilper, then we found that nozzle D is 240, and we can also solve for H. So we have different options, and we can see that they're going to give us different values. So that's an idea of how approximated is going to be our answer. So with those H, now we can use this equation to solve for the mean float, the mean temperature at the outlet. So U is equal to 1 divided by 10.2 plus 1 divided by 13.9. So we got 5.80 watts meter square Kelvin. Now the solving for the mean temperature on the outlet. So we have that the mean temperature at the outlet is equal to T infinity minus the difference in between T infinity and the mean temperature at the inlet, multiplied by E to the perimeter length U divided by the mass flow rate and Cp. So we replace all those values, and we got a temperature of 543 Celsius. So that's the temperature in the outlet. Okay, that's one of the answers. The second one is, what is the temperature on the surface? So for the temperature on the surface, we can use the standard resistance system, or a balance of energy in the pipe. So we have that all the energy that is coming from internal convection is going to the outside by external convection. So we have that Q double prime, so that energy is the same, is equal to the convection coefficient from the internal flow multiplied by the mean temperature in the exit, because we are analyzing the temperature at the exit, minus the temperature in the surface of the exit, and that should be equal to the external coefficient that we also found, multiplied by the difference in the temperature of the surface and T infinity, the surface at the exit and T infinity. Now, because we need to solve is for the mean temperature of the surface, so we have to distribute these factors and solve for TSO. So by multiplying H by these two factors, we obtain this, the same thing. We are distributing H, so you can review the algebra here. And then what we do is we're going to group TSO and TSO in one of the sides, and then factorize TSO and solve for TSO. So by solving for TSO, we get that the temperature of the surface and the exit is equal to 232. Now, how close we were from our guess? So in the first case, the temperature in the exit is 543, and our guess was 500. we are kind of close. The important thing is not how close is the temperature, but how much the properties change in time. So I will have to evaluate the properties in 520 and 43 and compare with these ones to know if we have a relatively high difference. If it's the case, so then we have to do a second iteration. And the same thing with the temperature in the surface that we said here, that was 500, which in reality is much lower than that, so we go 232. So that probably will be bigger change in that, and that will give us a better estimate of the exit temperatures. Okay, thank you.